Hi, welcome to your lesson on representation in probability. This is video 1 of 2, so please go on to the second video after this one. Let's begin. We have a situation where we have a class of 15 students, 3 study art, 6 study biology, of whom 1 studies art. That means one of the biology students also studies art. A student is chosen at random. We're going to let A represent the event. An art student has been chosen at random, and B represent that a biology student has been chosen at random. Now let's look at this first question. It says without sketching a Venn diagram, because in previous lessons we've made Venn diagrams to represent a lot of what we're talking about, but this one asks you to try without drawing a Venn diagram first. So find the probability of selecting each student. So what's the probability of selecting an art student? Okay, that probability of A, selecting an art student, is 3 out of 15 because we have 3 studying art out of the group of 15. So what's the probability of selecting a biology student? Oh, by the way, that one reduced to 1/5. Probability of selecting a biology student is 6 out of 15 because there are 6 biology students, and that reduces to 2/5. So hopefully those were easy. The numbers were right there given to you. And the Venn diagram was not really necessary. However, a Venn diagram can help. So it says, however, representing the information using a Venn diagram allows us to more easily see other important relationships. So although a Venn diagram sometimes is not necessary, like we saw, drawing it helps us make more, more complicated conclusions from the data. So let's take a look. Sketch a Venn diagram. And hopefully it looks something like this. So we have our art students. There are 3 of them in total. There are biology students, 6 of them in total. 1 student who studies art and biology goes here. Okay, that's the intersection. And then that means there must be 7 remaining out here because in total this is 8 students, so 7 more out here to make 15. Okay, next, now that we have the Venn diagram, it's important to notice that when we have a Venn diagram, we can write it like this with the amounts, or we can write it with the probability fractions already in there. So notice just all these numbers are kept the same, but all of them are going to be put in a fraction over 15 because there are 15 students in total, and that represents the probability of selecting one, like 2 students that are biology only here, 7 students that study neither, and so on, 7 out of 15. Okay, so now that we have that, we can use that to answer more things. So using the Venn diagram, find the probability, this one right here. So see if you can find that. Okay, for this one, it is important to remember what these symbols here mean, the little apostrophe. That means not, so, or the complement of A. So here we have the probability of things that are not A and, because intersection means and are not B. So things that are not in A and are not in B are the things that are outside here. So students that are not in art and not in biology, well, it's 7 out of 15. It's the students out here, the remaining 7 that study neither art nor biology. Okay, next question. Select from these 3 here, or from these representations below, the symbolic representations, find the ones that match these 3 here. So for example, for A, that 1/15, which is here, which of these represents that zone right there, and so on. Do that for all 3. Okay, so hopefully you got those matches to be correct. The 1/15 is the intersection, so the intersection's here. The 2/15 is A, but not B, because these people here are art students, but not biology, so that would be A intersection, not B. And then the 5/15, which is here, are biology students that are not art students, so that would be biology but not art. Where's that? Right here, not art and biology. Okay, great. Next thing we're going to do with this is this. Use the Venn diagram to find this probability. This one here, a little bit longer of a probability statement. All right, let's see how you did. So the answer to that is 6/15. And the reason for that is because these two combined basically represent the whole biology group, which is in total 6 out of 15. Let's look at that in pieces. So A intersection B means art and biology students. So that's the 1/15. And then not A and B means biology students that are not art students are these ones here. So basically this represented that student, This represents these students, and in total we have the whole B circle, so probability of B, and it's 6 out of 15. And that can be reduced to 2/5. Okay, now let's look at other representations, because we've really had a focus on Venn diagrams so far, but there's so many other ways to represent data or information in probability situations. So let's take a look. For example, if you have two events, so something like this, tossing two coins, coin 1, coin 2. So here are the possibilities when you toss coin 1, here are the possibilities when tossing coin 2, and here are represented all the possible things that could happen. For example, we could get a head on one coin and a head on the other coin, that's two heads. Or a head on one coin and a tail on the other, that's a head tail. And this represents the 4 possible outcomes when you toss two coins. There are only 4 options. So this kind of diagram is called either a two-way table or a sample space diagram, and basically it's a way of systematically representing all the possible outcomes so we can clearly see what all the possibilities are at one time. Another way to represent all the possible outcomes is using what's called a tree diagram, and we've seen these kind of as well, but a tree diagram represents one event after another after another. So here we have 2 events, tossing a coin and then tossing a second coin. So when you toss the first coin, it can be heads or tails, and then you toss the second coin, and now you go from, hey, if it was a head on the first coin, now we can get a head tail on the second coin, or it was a tail on the first coin, now we have a head tail on the second coin. So this diagram is kind of similar to this because it represents the 4 possibilities, and you can see the possibilities by tracing one path. So for example, you can go head, head, and that's like your double head situation, or head tail, and that's like a head tail situation, or tail head, or tail tail. So all the 4 outcomes are there as well when you follow the paths to their end. Okay, so looking at this some more, let's say we roll 2 dice, and we can make a sample space diagram for that as well. Here's a sample space diagram. Here's die number 1, you can roll 1 to 6. Here's die number 2, you can roll 1 to 6. And here we're going to call it like red die, blue die. And here's all the possible outcomes, right? You can roll a 1 and a 1, or a 1 and a 2, or for example, here's a 4 and a 3, or in this corner, you roll a 6 and a 6. So here's all the possibilities. And if you count them up, this is a 6 by 6 two-way table. We have 36 possible outcomes when you roll 2 dice. So 36 possibilities. That's a big sample space diagram, but still useful diagram when you're doing probability. This can also be represented like this, where you can say what is the sum of those. So for example, if you roll 1 and 1, that makes a score of 2. Or if you roll 6 and a 6, it makes a score of 12. So this is the same sample space diagram as here, but it shows all the sums. But also it's still a sample space diagram showing all the outcomes. Of course, we can show that on a tree diagram as well. We can have the first roll represented by the first branches here, so you can roll 1 to 6. And then if you roll 1 on the first die, then you can roll 1 to 6 also on the second die. So you can see all those options and all those options and all those, and all together, just like here we have 36 different options, here we have 36 different options as well. And you can see the sum is given there, which matches all these sums. So 2 very useful ways to represent probability are these 2 things right here. Okay, so now let's go to the next one. Let's say you had 3 or more events. So again, here you had 2 events. You roll 1 die, you roll another die. So a sample space diagram works. But if you had, let's say you rolled 3 dice, you could not show it on a sample space diagram because you would be, how could you show 3 things, right? This shows 2 things, 2 dimensions, but you cannot show it in 3 dimensions. So for 3 or more events, the sample space diagram is tough, but a tree diagram is still possible, right? Here's an example. You go to dinner, you choose a side dish, a main dish, and a dessert. So 1 branch for side dish, more branches from that for main dish, and more branches for dessert. You can show those 3 events like that. Okay, now let's look at this problem. So please read this and see if you can fill in the spots on this tree diagram. The way we fill in the tree diagram is along the branch we write the probability of that thing happening. In this case, a hit is getting a bullseye, a miss is not hitting the bullseye. So let's say fill in this part and this part. What goes here and here? Okay, let's check. Check your whole tree diagram, but we have, along with the ones I asked about, we have 0.8, 0.2. So you have a 0.8 chance of hitting the bullseye, and then this student is a very confident archer. No matter what happens here, they still have the same chance exactly on the next shot. So 0.8, 0.2 again. Okay, let's find some probabilities. What's the probability that this student gets 2 bullseyes? Well, that, as you may remember, when you're following a path, you just do hit and hit, right? Two bullseyes would be hit, hit, so you just multiply along the path. So multiply 0.8, 0.8, and you get your probability of two bullseyes. How about hits only one bullseye? Okay, this one's a little trickier because to hit one bullseye, there are two paths that get you there. For example, you hit the first bullseye and then you miss the next one. That path works, but also the path of missing your first one, hitting the second one, that works as well. So you have hit and miss, or, that means or, miss and hit. And in that case, we have hit miss is that, and here's miss hit, and you end up, when you add those up, you get 0.32. So that's an important point about tree diagrams. You can multiply along one path to get that probability, but if you want to find a combination of paths, you have to add them up. Okay, final question here. Let's say we want to hit at least one bullseye. So I'll show you how this one goes. At least one bullseye would mean one bullseye or two bullseyes. So this path works, or hit miss works, or miss hit works. The only path that doesn't meet this criteria is this path on the bottom, which is miss both times, miss miss. So in that case, it's easier to use what we call complementary events. Rather than adding up three possible paths, we can say, find out what's the probability along the one path that doesn't meet this situation, and then subtract it from 1, from the 100%. So probability of miss miss is 0.2, multiply those and subtract that from 1, and it gives you then the probability of all the other three paths, because all the paths in order will make a total of 1. Okay, here's a little bit of international mindedness, so please pause and read this. It's a really interesting piece of history for probability. Okay, and now let's try another problem. So read this problem and see if you can fill in these branches. So let's say, first of all, tell me what goes here and in these three spots. Okay, now check your work. Here's the Venn diagram completely filled in. If something didn't work out for you, take a look at the words again here and see if you can make sense of it. Okay, I think you can figure that out. Let's try some problems related to that. So find each probability. Let's try A. What's the probability of getting let's see, what would the R represent? R was some dice, right? Anyway, what's the probability of R then R? Okay, so the probability of getting two red dice is a half and a half, right? You just follow that path, half times half, which makes 1/4. How about a probability of blue and blue? Well, that one is 9/10, because for that one we followed 3/10, 3/10, multiply those, we get the blue path. And then green likewise is green path 1/5 times 1/5, which is 1/25. So those are the three paths that lead to getting the same color twice. And the situation here says to win, you have to choose two of the same color. So what's the probability of winning? Okay, well, to win, like I said, when you have multiple paths, so the three winning paths are these three paths, right? The red path, blue, and green. If any of those occurs, you win, because you get two colors of the same. So now you just add up those three paths, and you get the full probability of winning, all the three paths combined. And it is 38/100, or 0.38. All right, here's another way to represent that. This is an interesting representation, not that commonly used, but it's the same situation represented in a different kind of visual way, not a tree diagram. So take a look at this. Again, not very common, but pause the video now, look at this, read this, and see if you can make sense of the approach that was used here. It's kind of interesting. And now let's finish with this problem. So we have another situation. Please read that, and let's fill in, how about you fill in this one and these two. I'll do all of them, but for this question, do this one and these two. So for that, we have 3/6, and then there 3, 6, 1, 6, and all those are the same, because the main thing is here that the stone was replaced in the bag. So when it was put back in the bag, it's like the bag was reset, and the probabilities on your second draw from the bag are identical. So nothing has changed. Notice these are identical to the beginning ones. That's an important point we'll look at more later. So now this path leads to red-green. This path is green-red. And the question here was asking, what's the probability of finding red and a stone was, one was red, one was green? Well, there's one path, red-green, and another path, green-red, leads to that situation. So you take the two paths, add them up, and you get this value here. Add it up, it gives you this answer in the end. So two important ideas: multiply long paths and then add up to get the total. Great. Here's something to read. Pause and read this. And